So let's talk about Newton's laws of motion, right? So Newton's 3 laws of motion. I won't belabor the points too much because you should have some experience with these already. We're just going to go about some notation and some specificity. We're going to do them in a slightly different order than maybe you did them last year for reasons. So here we go, Newton's laws of motion. We said that Newton's laws of motion are valid in an inertial reference frame of reference. And our definition for that was a non-accelerated frame of reference. But really it was where all effects stem from causes, where we see something, see a force being applied and then an outcome of that force, or see the actors that are applying forces. We know where everything's coming from. We don't have those fictitious forces. Now, we will come back and talk about fictitious forces much more in Chapter 6. Chapter 5, though, is trying to frame everything out in inertial frames of reference. So here we go. Last year, you probably did Newton's first law, second law, third law. This year, we're going to start with Newton's second law, N2. And the reason why we talk about Newton's second law first is it's actually the central theme. Because we're going to find out that Newton's first law is merely just a specification of his second law. And just because of the mode of writing that was done in the 17th century, where you go to simpler situations and you build up to more complicated situations in terms of how you order your laws, that's the reason why they're presented as 1, 2, and 3, because 1 is talks about some more primal situation than 2, than 3, but everything is really based on Newton's second law in a lot of ways. So we'll start off with a sentence of Newton's second law, and I'm going to be upfront with you right now that this is not exactly Newton's second law, but it's our simplification for now. We'll rip the Band-Aid off a little bit later and go a bit when we get to another unit and go a bit deeper. But we will say that accelerations are caused by net forces. That's the basic idea, that accelerations, that changes in motion are caused by net forces, right? Not forces, net forces. Such that the acceleration is directly proportional to the net force and inversely proportional to the mass. There we go. Okay, now oftentimes this is presented rather than as a sentence, it's presented as an equation, and you may know that equation from last year where we said F net is equal to ma. Or the notation that we're going to use this year, rather than writing F net, we're going to use a slightly more advanced notation, and we're just going to use sigma. So this is the capital Greek letter S, or sigma F equals ma. Now, got to do a couple more things on that, because it's really important that we're emphasizing this year the vector nature of both the force, the net force, and the acceleration. But let's have a quick discussion about what net force is about, what sigma F is about, right? This is the vector sum of all the forces that act, right? Because if there's no net force, there's no acceleration. If there's a net force, there's an acceleration. And that's something also that people mess up. As long as there's a net force, that object will accelerate. It doesn't matter how large that mass is, right? If I have an elephant, if there's a net force on that elephant accelerates, right? It doesn't matter how heavy it is. It doesn't matter how massive it is. So in this role, let's just box this because that is going to be our statement of Newton's second law as an equation. We want to talk about the role of mass in this equation, as well as a couple of other things. The first thing is that we want to extend the idea of independence of dimension. Like we've been talking I hat and J hat. And I hat things can combine with other I hat things of the same type. And other J hat things can combine with other J hat things of the same type. And the same thing is here with forces, that I can only combine X forces to X forces, and Y forces to Y forces, Z forces to Z forces, theta forces to theta forces, radial forces to radial forces. The forces have got to be along the same axis for us to do that vector addition if we're going to be acknowledging this in a particular way. So I can write this as two separate statements, that F net X is equal to MAX. And let's say I'm using an X and Y axis. F net Y is equal to MAY. There we go. Now we're never going to really write those vector symbols above those forces and accelerations, except since we're doing theory here, that's why I'm going to focus on that. But we need to understand that it is really important that we can do these two things separately, independently, yet simultaneously, like we were talking about for projectile motion. And that is critical. And this structure is going to be critical to problem solving. We'll come back and talk about that at a later time. Now, just to verify something that we all know, net forces are composed of force. The unit for net force, and therefore the unit for force, is going to be equal to the unit for mass times the unit for acceleration. Hopefully you know this symbology from last year, that when you put a bracket around a variable, that you are saying the units of m and the units of a, right? And so this is a kilogram times a meter per second squared, and a kilogram times a meter per second squared comes up so often in physics that we call it the Newton. So that's our unit of force that we're using, right? Pounds, also a unit of force, but that's in the imperial system. We're not going to be talking about that. So here we go. The next thing I want to talk about Newton's second law is the role of mass in Newton's second law. So notice in Newton's second law, the size of the mass cannot prevent an object from accelerating, right? Even if it was, as long as a net force exists. As long as that number here on the left side of this equation is not 0, that object will accelerate, even if this is 10 to the 24th kilograms. It's just that this would be vanishingly small, okay? In a lot of ways, we're talking here about cause, net force, and then effect, and that is acceleration. So if I start talking about cause and effect, this is what I mean. So what role does mass play if net forces are the cause of change and the accelerations are the way it's demonstrated, the effect, that's what the change is? Well, mass acts to mitigate the effect of net forces. That's the way we want to think about it. Mass can't prevent anything from happening. Mass merely mitigates the effect of net forces. When the same net force acts on two masses, the one with the larger mass is affected less. They are both affected, but the mass determines the size of that effect, right? And those are the things that I wanted to talk about with Newton's second law, right? So notice here, when we're talking about Newton's second law, we're talking about change is occurring. There are net forces. Newton's first law actually is a special situation of Newton's second law. Newton's first law is entirely under the context of the net force being equal to 0. That means that the acceleration is equal to 0, right? And so that's super important. And in fact, Newton's first law, we're going to call this situation where an object is not accelerating, where an object's net force acting upon it is 0. This is going to be called equilibrium. Okay? Now notice this says acceleration is equal to 0. That doesn't mean at rest. This could mean that an object remains at rest, right? Don't say at rest, because if I'm at rest instantaneously, I might not have an acceleration of 0. We'd say it remains at rest, or we would say this object is at a constant velocity, right? Those are the two options. Well, here, remains at rest, this is a situation that is called static equilibrium. and this is a situation that's called dynamic equilibrium. So what it is Newton's first law describes what happens in a situation where the net force is equal to 0. So theoretically, as I said, it's just this subset of Newton's second law. But we often praise it as a first law because it establishes what equilibrium is. And that's really what it was in the 17th century, is that when scientists were writing these books, in their area of expertise, they would start off by describing the equilibrium condition for their science and then move on to the non-equilibrium conditions. The same thing happened in thermodynamics. They wrote the first and second and third law of thermodynamics, and then they were like, oh, hold on, we forgot to talk about equilibrium in thermodynamics, which is why they made the 0th law of thermodynamics to describe as the primary law the equilibrium state. So that's the reason for out of order. So here we go, as we know that this is a body at rest, remains at rest, unless a net external force acts. The key idea here is net. Let's just talk about external for a second. Right, like I'm a physical body here. Inside, like my heart is beating and there's intermolecular forces going on. We don't care about that. External is really about what the scope of the system that you're dealing with that is meaningful, okay? And so it's actually super important that we're gonna say, at least for now, all bodies that we are going to deal with are point masses, right? Even though like my arms can act independently of my body, that's not interesting yet for physics. So imagine a person as a point, right? Or a box as a point, a car as a point. We're not going to deal with all the individual parts moving because they're just a little bit too complex for us. When we get to chapter 10, or really the end of chapter 9, we'll start talking about things as beyond point masses. But for now, a very fundamental understanding is that all of our masses, for sake of everything else, are point masses. So that's going to like help us out with this external bit. And then we're going to say a body in motion will remain in motion at a constant velocity unless a net external force acts. Right? And it's really important that we actually say at a constant velocity, because a body in motion will remain in motion unless a net external force acts is not descriptive enough, because very specifically the Greeks, which in a lot of ways is what Galileo and Newton are responding to when they write their treatises, thought that the natural motion was the celestial motion of the planets going around, or rather, everything going around the Earth in perfect circles. That was the natural motion. So you don't want to just say remain in motion, because a very important thing at the time was establishing that the natural motion was this constant velocity motion. And remember, constant velocity, that doesn't just mean constant speed, but it also means a constant direction. Right? So something in a nonlinear path is really not obeying Newton's first law, because by definition, the direction of its velocity is changing. Right? Now, one component of it, like the x component, might be in equilibrium, but the object holistically would not be in equilibrium. So it's really important that we have all those phrasings down. Newton's first law is sometimes called his law of inertia, right? Therefore, we have the concept of inertia being, now some people want to say, an object's resistance to change in its motion. And that's problematic. So we're going to write that down as a problematic phrase. Actually, not an object, a mass's resistance to changes in its motion. The problem with this phrase is the idea of resistance, because it makes people think inertia is a force. Inertia is not a force. It's a tendency, right? It's the tendency of objects to persist in their straight line motion. That's actually the first idea that we have about inertia, is a mass's tendency to persist in its straight line constant velocity motion. But that's not really that, helpful of a concept, because that's just a different way of saying Newton's first law from the way we phrased it. There's nothing different there. It's also not quantifiable, because this tendency to persist in straight line motion, either it persists in the motion or it doesn't. But inertia is a quantifiable concept. It is quantified by mass, right? So an object with larger mass has a larger inertia. And so here is the important thing about the concept of inertia then. Even though we call Newton's first law the law of inertia, the quantifiable nature of inertia manifests itself in this mass there. Because if I solve the acceleration, I get net force over mass. We get this notion that the mass, as we said before, mitigates the effect of net forces. That's the quantifiable notion of inertia. It is the degree to which mass mitigates the effect of net forces. And notice the word mitigate is better there, because mitigate, when you mitigate something, you're never stopping it. What you're trying to do is lessen the severity of it. And that is a better vocabulary choice than the awful term of resistance that gets used above, because it leads to two conclusions. One, an object's mass can be big enough that it would prevent something from moving. No. A mass can never be big enough to prevent something from moving. The reason why things don't move when you push on them is because of static friction, not because of mass. Now, there's a relationship between static friction and mass, but it is a correlative one, not a causative one, and therefore putting this causation into the definition is intensely problematic. So here we go from here. Now let's go to Newton's third law, which people think means for every action there's an equal and opposite reaction. That's the way it's phrased when phrased poorly, right? So I'm going to write that in red. Right? But I'm actually back up for a second. Let's give it a name. It's called the law of interaction. Right? Because Newton's second law talks about what happens when there are net forces, objects accelerate. Newton's first law talks about when there are no net forces, right? When the net force is equal to 0, an object persists in the present state of straight line motion. That's a binary. It's either A or B, right? So the third law has to be about something entirely different, because there's no other options there. This talks about the fact that we need two things interacting in order to have forces at all. And it talks about the nature of those interactions. So the poor phrasing of the law of interaction is, for every action, there is an equal and opposite reaction. So let's talk about why this is poor. It's poor because if we look at the glass here on the table, and I draw a free body diagram of the glass on the table. Remember free body diagrams? These are these glorious diagrams that show the forces, and only the forces that act on an object. We'll talk about those explicitly in another video, and they're going to become the central part of your life for the next, several months. There are two forces acting on that glass sitting there. There's a force of gravity acting, and there's a normal force. Now, if you notice, I drew a dot in the center because, remember, we're pretending that all of our masses are point masses, so I wanted to draw all the forces acting concurrently at that point mass. Now, we are going to start to draw forces not acting from that point because later on it's going to matter where they actually act from on the object. So we'll talk about that in class. And there's that normal force, that support force from the ground that we were talking about. So for every action, there's an equal and opposite reaction. So what's the action? Gravity pulls down on the table, or down on the glass, causing the glass to interact with the table. Oh, therefore the table pushes up on the glass, right? And looking at that, yeah, these two forces are opposite in direction. Yeah, they're equal in magnitude because I know this thing is not accelerating. Therefore, the net force on it must be 0. So these two things are equal in magnitude. That's the way someone might say it, right? But if I were to write out what these forces are, this is the force of contact between the table of, or they're not between, but like of the table on the glass, right? And this is the force of gravity. And if I want to use the same phrasing, it's the force of gravity of the earth on the glass, okay? Now, just a casual interpretation of this, for every action there's an equal and opposite reaction. Action, gravity acts, causing it to pull into the table. Reaction, the table pushes up on the thing. Equal magnitude, opposite in direction. It's very easy to see that, oh yes, these two things are what Newton's third law must be talking about, but that is false. And there's a reason why it's false. I can have the force of gravity of the earth on the glass independently of this normal force. If I were to just hold this glass here and I drop it, clearly the force of gravity is acting on the glass, right? That force acted independently of the normal force. Same way here, let me just pick you up for a second, I can push personally the glass up against the table. Now, the reason why the glass is, in contact with the table has nothing to do with gravity, right? It has to do with the fact that I'm pushing it into it. So therefore, the force of contact with the table and the glass functions independently of the force of gravity on the glass due to the earth on the glass. So since those two things don't necessarily connect, like the existence of one doesn't imply the existence of the other, they're not talking about Newton's third law. So let's talk about what Newton's third law actually says. It says that all forces occur in action-reaction pairs, where the members of the pair have a couple of attributes. The first attribute of those pair is the existence of one force implies the existence of another force. Okay? So, like I was saying before, I can have the force of contact of the table and the glass even if there's no gravity. But what I can't have here is that if the glass is in contact with the table has to be in contact with the glass. Those two things are inextricably linked, right? So the force of, I probably should do this in green because this is a good thing, not the red. I'm not sure if I have a green pen. Do I have, is this in green ink left? Yes, green is good. Force of contact of the glass on the table. These two forces together make what's called a Newton's third law pair. Okay? The force of contact of the table and the glass, the force of contact of the glass and the table. The existence of one of those forces implies the existence of the other. The glass cannot be in contact with the table unless the table is in contact with the glass. Absolutely inextricably linked, right? Where the members of the pair, the grammar is terrible here, but we'll say are equal in magnitude, meaning the glass can't press more on the table than the table presses on the glass. Opposite in direction, or are opposite in direction, are opposite in direction. Okay. Next, you'll notice a very important distinction here. Another reason why the two forces in green, or rather in blue, couldn't be Newton's third law pair. This is the force of contact. That's a force of gravity. They have to be of the same type. Are of the same type. And the last thing is actually, in a lot of ways, the most subtle of the things. I asked before, what's the minimum, before meeting in class, what's the minimum necessity to ever get forces? And eventually we got to the answer is that we need 2 objects. And 5 here encodes that idea, right? Where the members of the pair act on the 2 objects interacting. One member acts on one object, the other member of the pair acts on the other object. So act on the 2 objects interacting, right? So one member of the pair on each object. Okay, right here, for example, one of the members of the pair acts on the glass, the other acts on the table, right? So what does that mean? Well, the consequence of this is that Newton's third law pair members can't cancel each other out. Other forces can cancel out that member of the pair. For example, the force of gravity of the earth on the glass is canceling out the force of contact of the table on the glass. But the force of contact of the glass on the table doesn't cancel out the force of contact of the table on the glass because they act on 2 different objects. That's like if I punch one person to the right and I punch one person to the left, saying like, oh, those cancel out. No, I'm going to jail twice for punching 2 different people, right? For 2 objects, for 2 forces to cancel out, they've got to act on the same object. And since by definition, Newton's third law is about the interaction of 2 things, a member of the pair acts on one on each object, those 2 forces can't cancel each other out, even if other forces end up canceling them out, right? And this is actually what Newton's third law is. It's all of this. And you can see how this has a lot of the same elements, but because you're trying to be pithy, you lose a lot, and it leads to misconception. So sometimes, folks, you need length and nuance, and trying to capture something in the smallest possible essence is not good. This is the smallest possible way to express the true nature of Newton's third law, right? So there it is, the law of interaction. Now, last year, you never really even dealt with the law of interaction beyond me asking, or someone asking you the question like, you're driving along and there's a fly and then boom, you hit the fly, right? Which experiences the larger force, the fly or the car? We want you to say the fly, right? Because we see the fly explode and the car is not affected. But Newton's third law says that those 2 forces are equal in magnitude. And that's really hard to understand because the fly is affected more. But the effect of forces on objects has to do with Newton's second law, right? And so we have to be very careful that Newton's third law is only talking about causes, not effects of those causes. The other thing is, last year, you did problems in which, like if I pushed on the table, we only ever looked at what was happening to the table. We never really talked about what was happening to me. We were only ever examining a system that had one body. So talking about the interaction between 2 bodies wasn't really meaningful. This year, most of our problems, after the first couple of problems we'll look at, will have 2 objects interacting through some mechanism. And therefore, Newton's third law, which is going to be a pair of forces where one member of the pair acts on the first object, another acts on the second object in opposite directions being equal magnitude, is going to be so much important this year as we look to more complex systems. But in simple systems, Newton's third law really doesn't come up. So there you go. That is the basics of Newton's laws of motion. And then the next thing we're going to do is we're going to put these things into practice and see how we can do them, do problems using primarily Newton's second law, although we'll be using understandings from the first and third law, even if we're not using them in a quantifiable way.